Next talk is by Professor Kai-Uwe Bux. I hope I'm pronouncing your name correctly, from University of Bielefeld. And he will speak on an alternative construction for the bordification of outer space. So over to you, Professor Bux.
Thank you very much. First order of business, I have to apologize for my video being offline. I don't want YouTube to know what I look like. I ask for your forgiveness. Second order of business, I'd like to congratulate Professor Raghunathan on the occasion of his 80th birthday. It's a tremendous honor to be a speaker at this conference, and I thank the organizers for inviting me. 1968, Invenciones published a paper by Professor Raghunathan with the deceptively modest title, A Note on Quotients of Real Algebraic Groups by Arithmetic Subgroups. And in that paper, he pushes a more theoretic point of view for reduction theory. At least that's how I think about it. And that point of view has informed much of my thinking. And to some degree, it'll show in today's talk. So this is about bordification of outer space. Let me start by giving you the overview. So we will be in this lecture talking about the right side of this slide, out Fn. Out Fn is an interesting group, the outer automorphism group of the free group. In order to understand it by geometric means, one looks at its action on outer space. And Mladen Besvina and Mark Fain have given a way to bordify that. This is parallel to the situation for GLNZ or SLNZ. There you look at the action on the symmetric space, and a bordification has been given by Borel and Serre, and an alternative construction has been provided by Grayson. The difference between the Borel-Serre construction and the Grayson construction is Borel and Serre add stuff at infinity. They add a boundary to the space. And Grayson pushes in from infinity, removes stuff near infinity, and what is left is a retraction, an equivariant retraction, deformation retraction. So what I will be discussing is joint work with Peter Smiley and Karen Vogtman, where we mimic Grayson's approach to give another construction for the bordification of outer space. So one thing to keep in mind is the philosophical similarity. So the symmetric space, the way I like to think about it, is as a moduli space for tori with a flat metric. And outer space is a moduli space for metric graphs. And the action of these groups is not by changing the metric and moving about in the space that way. It's by changing the way the fundamental group of that object, the torus on the left hand and the graph on the right hand, is identified with z to the n or fn respectively. So that's how these spaces work. So, oops, what happened? There. So first of all, what is outer space? You start with the rose. A rose is a graph that just has one vertex and n petals. So this is a rose. And the free group is just the fundamental group of that graph. And a connected graph has a contractible universal cover. So it's a classifying space for its fundamental group. And that means that the automorphisms of the free group can be described as self-homotopy equivalences of a graph up to homotopy. So these are the homotopy classes of self-homotopy equivalences. And that's the way to describe the automorphism of Fn. And oops, now I'm running out of space for a little bit. Just a sec. There we go. So outer space wants to consist of marked metric graphs. So what is a marking? A marking of a graph is an identification of its fundamental group with the free group. And the way to realize that topologically is to take a homotopy equivalence of the rows to the graph. And a metric on the graph is just a way of assigning length to the edges. Each edge gets a length greater than 0. We will later on vary these lengths, and then it will be interesting what happens if the length of an edge goes to 0. Well, then the edge sort of disappears, and well, that's a collapse of an edge, and that could change the fundamental group of gamma, or it could, or it doesn't, and different things will happen. The volume of a metric is just the sum of all edge lengths, and an isometry of a metric graph is just a graph isomorphism that preserves length. So this is all very natural. A point in outer space, and we will be working with reduced outer space, is a connected marked metric graph of volume 1. So all the edge lengths add up to 1, and the fundamental group of the graph is identified with the free group. The graph is supposed not to have terminal vertices, so no vertices of degree 1. And it's also not supposed to just subdivide edges, so no vertices of degree 2. And the term reduced refers to the condition that we also don't want separating edges. And now if I have two such gadgets, so gamma is a graph, G is a marking, and mu is a metric, and I have another graph, delta, H is a marking, and mu is a metric, then I need to say when they are equal, and they are equal, so they represent the same point in outer space, if there is an isometry between the two, such that if I look at the diagram given by the markings, so those are maps from the rows to gamma and to delta, that diagram is supposed to commute, but only up to homotopy, because my maps, my markings are also just up to homotopy. Those are equivalence classes, essentially. So that's what a point in outer space is. Oops, now I'm running out of Blackboard space. Never mind. So there we go. Here's a picture. So let's look at n equals 2. So here's the rows with 2 petals. I drew one of them in red and one of them in blue. And here are our metric graphs. So this is a graph with 3 edges. It's a theta graph. You can pretend that all the edges have the same length. So they are all length 1/3. And the labels, the loops, indicate how the homotopy equivalence is supposed to work. And here you have an edge. So here you just have a the rows again, but now one of these two petals is oriented differently, but because there's an isometry between the two, those actually represent the same point in outer space. And what you can see is if I take the middle edge here and make it shorter and shorter and shorter, what happens is that I approach this face. So each volume 1 metric on a graph is just barycentric coordinates for a point in a big simplex, right? And since all the lengths are supposed to be greater than 0, this is an open simplex. So outer space is just a collection of open simplices. And what this picture is supposed to indicate is which open simplex arise as faces of other open simplices. And in this picture, there's another thing interesting, namely what happens here at the corner. Well, in order to go there from the triangle, 2 edges have to go to 0 in length, but that would just leave you with the rows with 1 petal, and that has the wrong fundamental group, so it can't be there. So this is a face that is missing in outer space. We think of these as ideal faces or faces at infinity. So this is, the task of bordifying outer space is to invent stuff that can be glued in there. That's what this is all about. So just a little recap, moving in outer space happens by changing the metric. That's how you move within a simplex. If you change the metric and the edge length of a particular edge tends to 0, you move towards a face of that open simplex. And if collapsing the shrinking edge changes the fundamental group, that face is not actually in outer space. So here is 2 illustrations what happens. So this is what we have already seen. We have a theta graph, and if we shrink one of those 3 edges down to 0, we just approach a face. So here we have changing that. Here you could shrink another edge, and so on and so forth. So moving towards the edges means shrinking one of those 3 edges, but shrinking 2 of those edges, that takes you to infinity because it's no longer there. Here we have another triangle. In this case, we have n equals 3, and the triangle comes from a rose. And here, all the faces are at infinity. Because in a rose, if you make one of those petals shorter at the expense of the others, right? And you make it really short all the way. No, wait, just this is not approaching an edge. This is approaching a face. So I should put it there. Even if you just make one edge shorter and shorter and have it go to 0, you're still approaching infinity because collapsing a loop, deleting the loop will just change the fundamental group from F3 to F2. So that will take you outside of outer space. And the goal of bordifying outer space is to find a co-compact out of n space with finite stabilizers and you want it to be highly connected at infinity. So it will be highly connected very likely because outer space is contractible, and you want to add stuff at infinity to make it not just highly connected, but also highly connected at infinity. And you want finite stabilizers, right? So in order to make the space resemble the group as much as possible. So that's why the first idea that pops to mind after drawing these pictures won't work. So the first idea is, of course, to add in the ideal faces, right? Then clearly the complex would be co-compact mod the group, and everything would be nice, except stabilizers of ideal faces are not finite. So the stabilizer of a simplex in outer space is essentially the symmetry group of the graph, but the stabilizer of an ideal face that's in outer space also allowing you to take a face to a neighbor, to a neighbor, to a neighbor, just as long as you keep the vertex at infinity. So stabilizers would be too big for that idea. That's not a successful idea when it comes to bortifying outer space. So let me tell you what Mladen and Mark did. So you need to be more careful. You need to blow up the vertices at infinity. So here's how they do that. A core graph in gamma is a subgraph that can be written as a union of simple circles, finitely many simple circles. So for instance, in this one, the proper core graphs are, well, these are the simple circles, and everything you can write as a union of those are core graphs. So besides those, that's just the graph itself. And now you can take the open simplex that corresponds to the graph gamma, and you can map it to the product of closed simplices over all parametrized indexed by all the core graphs. And what you do is you take a metric, you restrict the metric to the core graph, and then you rescale it to 1. And afterwards, you take the family of all of those, so the tuple of all of those. And that will be an injective map on the simplex. And you take the closure of its image. And that will be the bordification of this open cell. And then you glue them all together to get the bordification of outer space. Let me show you the picture, what happens. So here's an example. Again, the theta graph. The theta graph is a core graph itself. So the first map is just the identity map, rescaling a volume 1 metric. Well, taking a volume 1 metric on gamma, restricting it to gamma doesn't change it. Rescaling it to volume 1 doesn't change it. So in the first coordinate, we just get the identity. And now we have these 3 other core graphs. And if you look at what the simplex of such a diagon is, well, that is just the unit interval, right? Because, well, what is a point in this interval? It corresponds to well, there are 2 lengths for each of these 2 edges, right? And they have to add up to 1, so you just get the barycentric coordinates of an interval. So that's one thing. And now you have these 3 intervals for each of these core graphs, for each of these circles. You have one interval. The product of these intervals is a unit cube, and it remains to, we still need to understand the map from the simplex to that cube. And here's what rescaling a metric after restricting it to a core graph will do for you. So it takes the triangle and it maps it to this weird surface kind of thing. So you can understand what the edges do. So what does the blue edge mean? The blue edge means the blue, so this side of the triangle is where the blue edge has gone to 0, has gotten very small in length. So the red and the black edge are the survivors, and where you end up on this blue edge is given by, well, how long is the black edge and how long is the red edge. And that will correspond to a point here on this edge, on this edge. So you have this coordinate in the unit cube, but you will be on the 0 face for the blue edge. So you are on the bottom edge down here. And similarly with the red edge, you end up at the top red edge. And this little vertex here that isn't there, the vertex at infinity, this vertex gets blown up to the yellow edge in the cube. And the way this works is, well, when you approach the yellow vertex at infinity, what does that mean? That means that the blue edge and the red edge both go to 0 in length, but they don't need to go to 0 at the same rate. They don't need to go to 0 at the same speed. So if the red edge is always 10 times longer than the blue edge, you will end up at a point up here. Not so sure about that, but anyway, so you will be close to the boundary because the red edge will remain 10 times larger than the blue edge, even in the limit. This is what you keep track of. So this keeps track of the direction in which you approach infinity, the direction from which you're coming. It's like the tangent cone at that point gets blown up. It's a blow up in the sense of algebraic geometry. And that is why this little vertex here gets blown up to an edge, and you would, and it is, it gets you a full-blown hexagon. Actually, I do have, we can see that here. So this gives you an idea of what that surface looks like. And if we rotate that cube so that we get a top view on that surface, you see the triangle gets blown up to a hexagon, and every other edge of that hexagon corresponds to a vertex of the original triangle, a vertex at infinity, and every other edge, those correspond to the finite faces of the triangle. So that's how you can visualize this thingy. So this is very much reminiscent of, maybe I stay on that page a little longer. So this is reminiscent of the Borel-Serre compactification, right? The way you think about this is when you approach infinity, that means a closed loop is going to 0 in length. The metric degenerates in a way that affects the fundamental group. That's the same way that you approach infinity in the symmetric space, right? Where you have a moduli space of flat tori. It means on that flat torus, you find it, you fix a geodesic loop, and the metric degenerates in the sense that that closed loop goes to zero, and that's the way you approach infinity. And the Borel-Serre compactification wants to keep track of various ratios, asking from which direction do I approach infinity? How do I go to infinity? And this Bestliner-Fein bordification of outer space is adding the very same information. It's using the same information to differentiate points at infinity. So that's something to keep in mind. So the alternative construction is inspired by Grayson's approach. Namely, instead of adding stuff at infinity, you want to remove a neighborhood of infinity. And now you have to be a little bit careful. We will just get to that. So how do you remove stuff at infinity? Well, first of all, you look at the infinite faces, and then you say, well, stay away from them. So you add a border saying, I shall not approach infinity closer than that, or closer than that, or closer than that. So that's what you do when you want to stay away from infinity. Now, we already saw that there are actually layers to infinity, right? There are triangles, all of whose faces are at infinity. And then there are vertices at infinity, and there are edges at infinity. And we want to stay away from infinity in a way. We want to shave off material. We want to shave off ideal faces in a way that after shaving off, the remaining solid body remembers that there was something like infinity in this direction. So these two pictures illustrate the difference. So here you shave off a lot from the vertices and far less from the edges. And what that means is, what that results in is that for the vertex, like the top vertex, there is still a face like the green, well, no, green is not good. Like the black one right here, this little face, that is a remainder, that is remembering that there was an ideal face in that simplex in that direction. And you also want that happens for the edges. So you want to remember everything. And this only happens when you're careful, because what could happen is that you shave off, say, equal amounts from the vertices and from the edges. But then after shaving off the vertices, everything looks fine, right? But then you shave off the edges. And when you shave off all the edges, the faces that told you the vertices are actually there are all gone. So you shaved off too much for the edges. So you need to come up with a rule that says how much material you shave off for each vertex, edge, two-face at infinity. And it's not too hard to write that down in such a way that if you shave off everything in a simplex, then a permutahedron remains. And that's exactly what we do. And here's a picture for how the construction works for n equals 3. And again, I have a picture that this is now more important because this is again 3 dimensions. So the graph that we're dealing with is this one. So the n equals 3, we have 4 edges. So the barycentric coordinates give us an open 3 simplex in which we move about. And there are two infinite faces, two faces, and there are two finite two faces. So you can collapse the green edge and that doesn't affect the fundamental group, and you can collapse the blue edge and it doesn't affect the fundamental group, but affecting the red, but collapsing the red or the pink edge will take you to infinity. So, oops, what happened? There we go. So this here is a view from the side. The view is you're viewing a finite face. So this is this front face here that now degenerates is a finite face. And you can see the Joule has a face inside that finite face. Similarly, the back, that's the face that degenerates now, I hope. Yeah, that also has a finite face. And the other faces are all infinite faces and they get shaved off. So the edge here gets shaved off, leading to that small quadrilateral. The edge in the bottom gets shaved off, leading to that bottom quadrilateral, and so on and so forth. We call these bodies that remain joules. And when you are careful and you make your rules about how much to shave off so that everything fits together nicely when you want to glue outer space out of those open simplices, and in this case out of those, and then the joules are subsets of those open simplices. So you want the gluings to work, and you can do that, and then you get Joule space. That's our alternative to the Borel-Serre compactification, to the Bestwiner-Fein compactification. So, and what happens, what you get is Joule space, and that's an equivariant deformation retract of outer space. In particular, it's contractible. So it's a nice space. What can these spaces be used for? So Bestwiner and Fein proved about their bordification of outer space that it is 2n-5 connected at infinity. And that implies that out of n is 2n-5 connected at infinity. It doesn't directly imply that because the action of out of n on the bordification is not free, but the stabilizers are finite and out of n is virtually torsion free, and one can go from there. Also, as a consequence, they obtain that out of n is a virtual duality group of dimension 2n-3. And this, of course, is essentially just carrying out part of the program again from the Borel-Serre compactification, right? This is what you use the bordification for. The Borel-Serre compactification, wait, I'm going to get to that anyway. So let's see. I already remarked on that. So the point here is that out of n, so B follows from A by means of, so what is that torsion-free normal subgroup of finite index? So if you look at out of n and you project to GLNZ, and then you project to GLN Z mod 3Z, then the kernel of the composition, this is a finite group, right? So the kernel of that composition is a subgroup of finite index in out of n, and it's a classical theorem that that subgroup is torsion-free. And for the virtual duality group property, one also needs to know that the virtual cohomological dimension of out of n is 2n minus 3. That's a result by Color and Vogtman. And then you need to understand what the compactly supported cohomology for the bordification, or a free, well, yeah, for the bordification, what that thing is. And you need to know that it's concentrated in dimension 2n minus 3, and you need to know that it's a free abelian group. And these two items, Bespina and Fein do via combinatorial Morse theory. So what do we add to the picture? Well,
Professor Bux, the time is over.
Oh, the time is over. Okay, then, oh, sorry about that. Let me just wrap this up. So okay. We add that Rose complex is 2n minus 5 connected, which is a relative for outer space. It's the nerve of the cover of outer space by stars of roses. As a consequence, Joule space is also 2n minus 5 connected, and there is a direct proof for that that is a little bit simpler than what Bespina and Fein did. And Joule space is equivalently homeomorphic to their bordification. So actually, this is really just, this is not a new space. This is a new construction of their space. So in particular, this is an independent proof that it is 2n minus 5 connected at infinity. That happens to be simpler. Moreover, Joule space is easier to understand topologically. So for instance, these hexagons that I drew in the Bespina-Fein setting, in general, it's not so easy to see that those are even cells, like topologically, like PL balls. In our construction, that is obvious, and showing that these two spaces are homeomorphic is the simplest proof I know that the cells of Bespina and Fein are actually cells. So let me stop here, and I thank you very much.
Thank you very much, Professor Bux.
Sorry for going over time.
Few questions.
Yeah.
Yes, Mahan?
Yeah. So, yes, this seems to be basically a generalization of this manifold with corners thing for, say locally symmetric spaces and then taking its universal cover. Is that what you're generalizing here?
Yes. Yes.
Okay.
Except that the problem is, of course, that,
this is
that
not
outer
a manifold.
space is not a manifold.
Right.
And,
right.
And that's why half of the picture is missing. So in the symmetric space setting, you can use this to actually write down a topological source for the dualizing module.
Right.
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 You get the boundary at infinity, and it's a spherical building, and this wedge of spheres that shows the homology is concentrated in a single dimension, and you see, oh, that the homology of that thing is my dualizing module. But that requires Poincare duality, and we don't have that far.
Right. And could you say a word about, I mean, what exactly is the care that you take? I mean, just sort of heuristically, I mean, the shaving off being around the edges being,
right. You decrease exponentially.
Okay.
So you shave off epsilon in the vertices, epsilon square for the edges, epsilon cubed for the faces.
I see. Okay, thank you. Thank you.
Something like that.
Yeah, thank you. Yeah.
Any other question? Okay, I don't see any further questions. So let us thank Professor Bux for his interesting talk, and we will clap.
Thank you very much.